at the last part of our Chapter 5B unit, and that is over our sum and difference formulas. Now, with our sum and difference formulas, we have 6 different types, and that's because we have an addition and subtraction for each of our 3 main trig functions. Now, you do not need to have these memorized. I will give them to you on your test. You just need to know how to apply them. So make sure that you go ahead and snap a picture or write these down real quick, just so that you have reference to them as you're working on these examples in the notes, but also in your homework. These are also in your book if you need to refer back to them. So the whole reason why we need our sum and difference formulas is because up until now, if an angle hasn't been on our unit circle, we haven't been able to evaluate it. So in this case, we have pi over 12, and pi over 12 is not on our unit circle. And the key thing here is that not just that they ask us to evaluate it, because if they just ask us to evaluate it, we can plug it into our calculator and get a decimal approximation. The bigger thing here is that they specifically ask us to find the exact value. And because they ask us to find the exact value, we can't just give them a decimal approximation. And so this is where our sum or difference comes into play. So we have pi over 12. So we're going to try and find 2 sets of angles that when we add or subtract them, we get pi over 12. Now, the key here is that we want those 2 things to add or subtract to be from our unit circle. And so if we think about it, we could try and use like pi's over 6's, but if I like add pi over 6 plus pi over 6, right, that would give me 2 pi over 6, which would just be pi over 3, so that doesn't work. But we could try something more like subtraction. So again, if I wanted to use a pi over 6, if we think about it, I could try it with like maybe a pi over 4. But remember that pi over 4 is going to be bigger than pi over 6. So we don't want to do pi over 6 minus pi over 4 because that would give us a negative angle. We want to do pi over 4 minus pi over 6. And notice that if we find a common denominator, it would be 12. So we would have to multiply our first one by 3. And our second one by 2. And we do indeed end up with pi over 12. So basically what we're going to do to evaluate sine of pi over 12 is substitute that pi over 12 for whatever we found to add or subtract to it, which in this case was the pi over 4 minus pi over 6. Now, please be careful, because remember that none of our trig functions have a distributive property. So I can't just take sine of pi over 4 and subtract sine of pi over 6. It would be really, really nice if we could, but we don't have a property that does that. That's the whole reason why we have to have these sum and difference formulas, is because it's not that easy, and we don't have a distributive property. So please, in the future, when we're on our homework, and especially when we're on our test, remember that we cannot distribute any of our trig functions. But what we can do is apply our formula. So I'm going to look back and say, okay, I'm looking at my sine, so that's these first 2. We are using subtraction, so that's going to be the second one. And notice here that our sine has the same sign as the original. So think S same. Our cosine has the opposite sign of the original once we apply the formula. So think cosine has an O, so opposite. And then notice that sine is sine times cosine. for both of the terms, whereas cosine is cosine, cosine, and then sine, sine. So we're going to apply that formula. I'm going to use my pi over 4 as my u and my pi over 6 as my v. So I get sine of pi over 4 times cosine of pi over 6. Again, it's going to be the same sign, so we are going to have subtraction. And then I have cosine of pi over 4 times sine of pi over 6. Well, now notice pi over 4 and pi over 6 are on our unit circle, and so we can evaluate these now. And that's the whole reason why we use these properties or these theorems, is because now we can evaluate just using our unit circle. So hopefully we recall that both sine and cosine of pi over 4 are going to be the square root of 2 over 2. Cosine of pi over 6 is going to be the square root of 3 over 2. And then sine of pi over 6 is going to be 1/2. So recall that when I multiply two radicals together, as long as they have the same index, I'm allowed to multiply them. So square root of 2 times square root of 3 gives me the square root of 6. Then in my denominator, I have 2 times 2, which is 4. Then we have minus a square root of 2 divided by 4. Since they have a common denominator, I can combine them to be one fraction, but please be careful, because remember that we do not have a subtraction property the same way that we have a multiplication property. In order to be able to add or subtract radicals, we have to have the same radicand, which is the stuff on the inside. And since here I have a 6 and a 2, I can't simplify those, and so that would be my final answer. Now, if you wanted to go back and check yourself, you could plug sine of pi over 12 into your calculator. It's going to give you a decimal. And then you could also plug in square root of 6 minus square root of 2, all divided by 4 into your calculator, and it will also give you a decimal, and they should be the same decimal. So that is one way that you can kind of go back and check yourself. So let's look at another one. This time we're given to it in degrees, which is fine. We have cosine this time. So again, we're coming over to the side, and I'm thinking, okay, 75 degrees. I need two things that add or subtract to give me 75. Well, at least for me, I see 30 degrees plus 45 degrees pretty quickly. Now, the more that we do these, the better that you get at picking those two numbers. And that by far is not the only option. You could also do 135 degrees minus 60 degrees. There's going to be different combinations, and as long as you apply your theorem correctly, you will end up with the same answer. So whichever one you see first, just go ahead and go with that one, because like I said, you'll end up with the same answer. So looking at cosine of 75 degrees, like I said before, we're going to use that 30 degrees plus 45 degrees to break apart our 75. And then we're going to apply our cosine theorem. And so here we would have cosine of 30 degrees times cosine of 45 degrees. Remember that it's the opposite sign, so because I have addition on the inside of my parentheses, I'm going to have subtraction whenever I have my two terms separated. And then I'm going to have sine of 30 degrees times sine of 45 degrees. And then again from there, it's just using our unit circle. And so our unit circle is going to be very, very important that we know it. So we have cosine of 30 degrees, so that's going to be the square root of 3 over 2. Cosine of 45 degrees is going to be the square root of 2 over 2. Sine of 30 is 1/2, and sine of 45 is the square root of 2 over 2. So again, notice that we're going to end up with a square root of 6 minus the square root of 2 both over 4. And we can combine them then to be the square root of 6 minus the square root of 2 all over 4. Now, a lot of our answers are going to look very similar because remember that when we're dealing with our unit circle, we only have a couple of different values that we end up getting. And those are going to be 0 and 1, the square root of 2 over 2, the square root of 3 over 2, and 1/2. So we're basically just looking at different combinations of those. And so your answers are all going to look very similar when applying these theorems. So let's look at another example. Alright, so on this one, it says to find the exact values of sine, cosine, and tangent given that information. So I have 165 degrees, but this time I actually told you what 2 degrees I want you to use. So instead of you having to figure out what degrees you should use, I said I want you to use 135 degrees plus 30 degrees, which makes it a little bit nicer because then we don't have to spend the time figuring out what combination we need. And so some of your questions will have that, but you do need to get into a good practice of being able to find your combinations whenever it asks you. So here it says find sine of 165 degrees. So again, I'm going to break it apart just like we did before with that 135 and 30 because that's what they give us. And then I'm just going to apply my formula. So we have sine of 135 degrees times cosine of 30 degrees. It's going to be addition because it's the same sign. And then I flip them. So cosine of 135 degrees times sine of 30 degrees. And then we're just evaluating. So sine of 135 degrees, well 135 has a reference angle of 45, so I end up with the square root of 2 over 2. Cosine of 30 degrees is going to be the square root of 3 over 2. But be careful in the next one because remember that 135 is in our second quadrant, which means that cosine is going to be the square root of 2 over 2, but because it's in our second quadrant, it's going to be negative square root of 2 over 2. So remember, just like before, I'm going to end up with a square root of 6, but this time we're going to be subtracting that square root of 2. Next up, we're looking at our cosine. Again, we're using that same 2 numbers that they gave us. So 135 and 30. And then just applying my formula. So we have cosine of 135 times cosine of 30. Remember, it's the opposite sign, so I'm going to subtract. So sine of 135 times sine of 30. And then we just apply that unit circle. So I get a negative square root of 2 over 2 times square root of 3 over 2 minus positive square root of 2 over 2 times 1/2. So this time we get a negative square root of 6 minus the square root of 2 all over 4. And again, those answers look very similar, again, because we're looking at those different combinations of the same types of numbers. So that's why it's going to be very, very important that we don't drop negatives or positives anywhere. So we want to keep those signs, S-I-G-N, consistent. Alright, so on our next one, we're going to look at our last one, and we haven't seen an example of tangent yet. It's going to be the same in the fact that I'm just applying that formula, but my formula is a little bit different. And so it's going to end up requiring a few more steps to simplify. So again, we're still just breaking it apart like we did with our other ones. So 135 plus 30. But tangent, just like any of my other trig functions, is not distributive. So we cannot distribute the tangent. So we need to go back to our tangent formula and see, oh, okay, look, I'm adding here. So I'm going to have tangent of u plus tangent of v all divided by 1 minus tangent of u times tangent of v. So in this case, my u is going to be 135 degrees. My v is going to be 30 degrees. And I just plug everything in. Now remember that tangent is a little bit different because it's not strictly on our unit circle. So we do have to do a little bit of work in order to figure out what tangent is going to be. So remember that tangent of theta is equal to sine over cosine. So for my tangent of 135 degrees, my sine and my cosine are both going to be the square root of 2 over 2. Just my cosine is going to be negative. And so notice that that's going to be a negative 1. So that's pretty straightforward. My other one, however, recall at 30 is going to be 1/2 divided by the square root of 3 over 2. So we're going to have to use our complex fraction simplification. So remember, that's where we're going to keep our top fraction, change to multiplication, and flip our bottom fraction. So notice that our 2's are going to reduce. So I end up with 1 over the square root of 3. But we don't want to quite leave it like that. So we would multiply by the square root of 3 over the square root of 3, and we would get square root of 3 over 3. And then we can just plug those values in. So we get negative 1 plus the square root of 3 over 3 divided by 1 minus negative 1 times the square root of 3 over 3. Just going ahead and simplifying. In my denominator, I would get a negative square root of 3 over 3, but because we're subtracting it, that's going to become a positive square root of 3 over 3. Now please be careful here, because remember that all of my algebra rules still apply. Which means that I can't just start crossing out square roots of 3's or crossing out 1's, because we have addition in between and not multiplication. Also realize that we can't just factor out a negative from the top, because if we did that, then we would still have 1 minus square root of 3 over 3 on the inside of our parentheses, and so it still wouldn't reduce. So in order to be able to simplify, we need it to look like a complex fraction where we only have 1 fraction on top and 1 fraction on bottom, kind of like we did with our tangent. So in order to do that, I need to find a common denominator. So notice that I already have a 3 in the top and the bottom. So my negative 1 is going to become negative 3 over 3, and my 1 would be 3 over 3. So using that idea, we can combine those then to be negative 3 plus the square root of 3 over 3, and 3 plus the square root of 3 over 3. And again, using that same knowledge of our complex fractions, remember that we keep our first fraction, we change to multiplication, and we flip our second fraction. So then notice here that my 3's are going to reduce because they don't have addition or subtraction with them. So then I have negative 3 plus the square root of 3, all divided by 3 plus the square root of 3. Now again, please be careful. We can't just start reducing out some square roots of 3's or our 3's because we still have addition there. Now I'm going going to go ahead and stop there and say that's going to be my final answer. But some of you might have noticed that we have a square root in our denominator. And that's okay. In the past, we've always said that, you can never have a square root. And most of the time, that's going to be the case. But when we have something that's complicated like this, and we have square roots in both the top and the bottom, we're going to go ahead and leave it like that. If you wanted to rationalize it and get that square root out, remember you would have to multiply by the conjugate, which is going to be 3 minus the square root of 3. And you would have to do that to the top and the bottom. And that is what your book is going to do. So if you're trying to check your answers, just realize that that's what your book is doing. And so that's why their answer might look slightly different than what your answer looks like. So like I said, our tangent ones are a little bit different. So you're going to need to make sure that you especially look at those on your homework and on the practice that we have, just to make sure that you kind of get the hang of them and that you can find them like you're supposed to. Alright, so in our next one, these are all degrees. So we have sine of 42 degrees times cosine of 12 degrees minus cosine of 42 degrees times sine of 12 degrees. So this one looks a little bit different because we don't just have one trig function that they're asking us to evaluate. Also notice that neither 42 nor 12 are on our unit circle. And so we might be thinking, oh, I have to apply it a bunch of times this time. But that's not quite the case because notice the pattern. We have sine times cosine minus, and then my cosine and my sine have switched. So hopefully we can kind of see that that's actually the right side of our equation this time for our sine sum and difference formula. So remember that we have an equal sign there, which means that it goes both ways. So sometimes we need to use our sum and difference formulas to break things apart, but other times we might actually need to use them to pull things together and combine them. So like I said, this is our sine formula because we have sine times cosine. And remember with our sine formula, it is the same sign, so I'm going to have subtraction. So it's going to be sine of 42 degrees minus 12 degrees. Well, that's going to be sine of 30 degrees. And from there, we should know that is just 1/2. And so that would be my answer. So that would be an easy way for me to make sure that you know how to apply your formula is by giving you something that's on the right side of one of your equations and having you work in the opposite direction instead. And then we have one last way that we can kind of look at our sum and difference, and that's helping us to prove some of our previous identities. So this was one of our co-functions identities, and it is cosine of pi over 2 minus x equals sine of x. And before, we just said, okay, this is an identity. We didn't try and prove it or anything like that. But now, because notice that on the inside of my left-hand side, we have subtraction, we can actually apply our cosine subtraction formula, and we should end up with sine. And just because we have an x there, that doesn't change anything. Pi over 2 is going to be in the place of my u, and x is going to be in the place of my v. So I'm still going to apply my formula the same way. So we have cosine of pi over 2 times cosine of x. And remember, it's the opposite sign, so we have plus sine of pi over 2 times sine of x. And again, thinking back to our unit circle, recall that cosine of pi over 2, so cosine of pi over 2 is going to be 0, and then we have times cosine of x. Then sine of pi over 2 is going to be 1 times sine of x. Well, anything times 0 is going to be 0. Anything times 1 is going to be itself. So notice that we do indeed get sine of x. So you might see some questions and homework problems where it's actually asking you to help prove some identities using your sum or difference formulas. But remember that you apply the formulas the same ways. You might just have a variable inside of one of your trig functions instead, and that's okay. Alright, now the last set of formulas that we're going to look at is going to be our double angle formula. And basically this is just, like I said, another tool that helps us to be able to evaluate different types of numbers. Now, realize that this is by far not the last theorem or formula for our trig functions. There's actually a lot. We have half-angle formulas, we have power-reducing formulas. There are others out there. But I've given you the tools now to look at a question, and if you're given a formula, you should be able to apply it. Whether you've used that formula in the past or not, if it's given to you, you should be able to use it. And that's why we're not spending a ton of time on these last couple of formulas, is because I'm just showing you, like, okay, looking at a new formula, how might we apply this? That way you can use that same idea in the future if you're ever given a different formula that you need to use. So notice that we're given 4 times cosine squared x minus 2. And I want us to simplify. Okay? So notice that my first thing that I see is that I can factor out a 2 from both of those. So if I factor out a 2, we're left with 2 cosine squared of x minus 1. And you might think, oh, that's our Pythagorean identity. But be careful, because that 2 is with our cosine squared. So we can't just get rid of the 2 or just stick a 2 in front, because my 1 doesn't have a 2 either. So we can see that it's not our Pythagorean identity. So we need to think, okay, is there another identity that we can use? Well, lucky for us, we just learned a new one. So notice on the right-hand side, we have this cosine of 2u, and it looks kind of funky because we have 3 different equal signs there, and really there should be 3 equations. They just got kind of lazy. So cosine of 2u actually equals all 3 of these things. And so depending on the situation, you might have to use different ones. So in this case, cosine of 2u equals 2 cosine squared of u minus 1, which, if we notice, is what we have here. So we can say that this is 2 cosine of 2x. And that would be our final answer. So this is just, again, another identity that we can use to help us simplify trig expressions. Now, it can also be a way that we can find values. Now, please be careful here. So it asks us to find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. And a lot of people's first reaction is just to take 5/13 and multiply it by 2 and get 10/13. But notice that that 2 is on the inside of my theta. It's not on the outside, which means that I'm not multiplying my final answer, the 5/13 by 2. I'm multiplying the angle by 2 before I evaluate it. And so it's not as easy as just multiplying by 2. And since they tell us that cosine of theta equals 5/13, but they don't tell us what our angle is, we can't multiply our angle by 2 either. And that's where these identities come into play. So notice that we have these 3 different options for cosine, and then we have a sine of 2u and tangent of 2u. Well, notice that for my sine of 2u, we would need to be able to find, or we would have to have sine and cosine. And right now we only have cosine, so we can't use that one. And then over here, if we notice, on my other ones, I do have a one option that gives me just cosine of 2u, and that's by plugging into cosine squared of u minus 1. So that same one that we just used. So we know that cosine of 2 theta equals 2 cosine squared of theta minus 1. And so we can plug in our cosine of theta. So we have 2 times 5 over 13 squared minus 1. Well, 5 over 13 squared is going to be 25 over 169 minus 1, which is 50 over 169 minus 1. Then we would need to find a common denominator, which is going to be 169 over 169. So we would do 50 minus 169 is going to give us negative 119 over 169. Well, we end up with a negative. Is that okay? Well, if we look at where theta is located, it tells us that it's in our 4th quadrant. But realize that that doesn't really tell us a whole lot about 2 theta. So yeah, if we end up with a negative, then we're just going to leave that negative there. So now we have cosine of 2 theta. But like we said, we can't just use and multiply by 2. And so now I found cosine of 2 theta. But notice that for my sine of 2 theta, it requires us to know sine and cosine. We have cosine of u, but we don't have sine of u. And so as of right now, we can't apply that formula. However, let's think back. If I know that cosine of theta equals 5 over 13, well, let's think. Cosine of theta is adjacent over hypotenuse, which means that if this is my theta, we could do our opposite is going to be our adjacent is going to be 5, and our hypotenuse is going to be 13. And then we could use our Pythagorean identity to find our opposite side, because then we could find what sine of theta is by knowing our opposite over our hypotenuse. So remember that we would have x squared, or our opposite squared, plus 25 equals 169. Well, 169 minus 25 gives us 144. And the square root of 144 is going to be 12. So we know that sine of theta is going to be 12 over 13. And again, that's just sine of theta. But they don't ask us to find sine of theta. They ask us to find sine of 2 theta. And again, we can't just multiply by 2. We need to use that formula that we had on the previous page. So sine of 2 theta equals 2 times sine of theta times cosine of theta. And now, since we have both of those, we can plug those in. So we have 12 divided by 13 times 5 divided by 13. The only thing that we need to think about before we continue on is remember that I said that our theta is in our 4th quadrant. which is why we have a positive cosine. So technically, when I took the square root here, remember that I end up with a plus or a minus. So if our theta is in our fourth quadrant, we need to choose our negative 12 because we would need a negative for our sine. So this would be a negative 12, which is important because, again, we don't know what quadrant our 2 theta is in, so we're relying on the signs, SIGN, of our original functions to determine if our 2 thetas are positive or negative. So we would want to multiply straight across. So notice that 2 times 5 gives me 10, 10 times 12 gives me 120, and then 13 times 13 gives me 169. And so notice that neither my cosine nor my sine, just multiplying by 2, would not give me what my sine of 2 theta or my cosine of 2 theta is. It's very, very different. And that's why we cannot just multiply the original fraction by 2. Now, our last one is tangent. And notice it's a little bit trickier because it has tangent of u divided by tangent, or 1 minus tangent squared of u. So it's a fraction, and it's not a super nice fraction. It's not unheard of. We could use the same thing that we did before and say, okay, I have this triangle. We could find tangent of u now, which is going to be opposite over adjacent, which is 12 over 5, and apply the formula the same way we did the other ones. Or, because now we have sine and cosine of 2 theta, as long as we are consistent, tangent of 2 theta is still going to equal sine of 2 theta divided by cosine of 2 theta. And since we have both of those now, we can go ahead and just put those in. So my sine, we said, was negative 120 divided by 169. And my cosine is negative 119 divided by 169. I have a negative divided by a negative, so we will end up with a positive. We have a complex fraction, so again, we're going to need to keep the top fraction, change to multiplication, and then flip our bottom fraction. So notice that my 169ths reduce, and I end up with 120 divided by 119. And now we have found all 3 of our trig functions that it asked for. And again, like I said, this was an example of how to use your double angle theorems, but they could ask you, or I could ask you, or your book could ask you, to use some of your other identities. And you might see other types of identities in the future. But now that we've gone over this process, we should still be able to apply any identity or theorem that we're given.